Hi and welcome to MSc. In this video we're going to be looking at VSEPR theory, specifically the examples where we have 4 electron domains around the central atom. When we have 4 electron domains around the central atom, there's 3 cases that we need to work through. I will do one example for each case in this video. The first case, just like all the others, is always that all of the electron domains are bonding domains. Again, a bonding domain can be a single, double, or triple bond, and there will be no lone pairs. So a very common example here is methane. And methane is fairly straightforward to draw. Often you'll see it sketched in organic chemistry just like this. This gives it the impression that it's a flat molecule that's shaped like kind of like a square, which can be misleading, and that's why you'll see other types of illustrations sometimes in organics where they want to show the angle and positions of the atoms in more detail. So let's take a look here at what this actually looks like, and I'm going to use the PhET simulation for that. Here this is from what we were working from before with the trigonal planar, and I'm going to add in an extra bonding domain. So now I have 4 bonding domains, and you can see that it's drawn out like this, and this is actually what's called a tetrahedral shape. Notice all the bond angles are identical. They move around when I pull on them, but they're all 109.5. And we have 4 electron domains, and they're all bonding domains. So how this is sometimes illustrated then is we can do a picture where we have 2 of the atoms in the plane of the page, and then we have a wedge to show that one is coming out of the page, and then you can use a series of dots or dashes to show that another one is disappearing in behind. That's to try to give the impression of the 3D picture, just like here. See if I can rearrange this. We have 2 in the plane of the page here, and we have 1 in behind and 1 coming out. So our model looks like this, and we know that all the angles between all of these hydrogen atoms are all 109.5. It is tough to draw this properly so that you can see that all these angles, they're all 109.5, and the angle between these 2 here is also 109.5. So the methane will have an electron arrangement that is tetrahedral. So the domain geometry is tetrahedral because there's 4 electron domains. That will always be true for all these examples for 4 electron domains. Its molecular geometry will also be tetrahedral, and that's because all of the electron domains are bonding domains. Lastly, the hybridization on this carbon is sp3. That means you have 1 s orbital and 3 p orbitals all hybridizing together to form this structure in 3D space. So that's the first scenario where we have 4 bonding domains for methane. Now we move into case 2, where we have 3 bonding domains and 1 lone pair. So let's take a look through this one. Here we have NH3, and we can look at trying to draw this out. We know that nitrogen has 5 electrons in the valence level, and the hydrogens each bring 1, which is a grand total of 8. And you might draw it like this and try to space the hydrogens out. Again, to try to draw them in 3D space, that's not a horrible idea. We understand that hydrogen is a bit of an exception to the octet rule. Well, it's quite happy by just sharing 2. But by drawing it like this, we only drew 2, 4, 6 electrons. We have to remember the extra lone pair, and I find that students often forget that lone pair on the nitrogen, which is why doing something simple like a calculation here of the valence electrons available for bonding is so important when you're drawing the Lewis formulas. So don't forget those lone pair, they're super important. So from this, we know that we're still going to have the same electron domain geometry as we did with 4 bonding domains, because the electron domain geometry does not change through these scenarios. So it will have that tetrahedral overall arrangement of these 4 electron domains with the lone pair. The actual shape is something that's called trigonal pyramidal. So let's go back to a PhET simulation to really see what that looks like properly in 3D space. So here what I want to do is I want to remove one of my bonds and add a lone pair. And here we can see my molecule. This is in the model version, You can see the lone pair on top, and so we get this like triangular based pyramid. Thus, trigonal pyramidal is the shape. If we go over to real molecules and we look at this example here, then we can say that the actual bond angles get compressed to 107.8. And that's because of the presence of this lone pair on top with the higher electron density is pushing these other ones down together a little bit closer. So 107.8 is the actual bond angle for the ammonia. So back in our note, we can make a picture of this that looks a little bit better by saying, okay, well, I have a hydrogen here in the plane of the page. I have a hydrogen that's coming out of the page, and then I have a hydrogen that's disappearing in behind. And we can't forget the lone pair on top. The actual angles here are 107.8. Again, I don't think it's necessary to remember that angle, though your teacher might have you memorize it. It's more important to know that the angle here and behind those two will also be just less than 109.5. And remember that that hybridization on that nitrogen, even though it only has 3 bonds, is still sp3 hybridization. The last example I'd like to do for you is water. And we're probably fairly used to drawing out water in a bent shape, looking like this. Again, it's important to remember those lone pairs on the oxygen. So, what do we know about this one? Well, we know that the electron domain geometry is still going to be tetrahedral. Again, that is because of the 4 electron domains and their arrangement of the 2 lone pairs and those bonds in 3D space. As I mentioned at the start of this, we're used to drawing this as a bent shape, right? And it has that same structure. So we've seen this now getting bent molecules both from 3 electron domains and from 4 electron domains, depending on how many bonds and lone pairs we have. And the hybridization is still going to be sp3 on the oxygen. We can look to a simulation to see what this looks like. And we can go straight to a water molecule with its 2 lone pairs and its 2 bonding pairs. And we can see that we have those up top. It has this bent shape, and the angle has been further compressed to 104.5. This again depends on your teacher, whether or not you need to memorize the bond angles. I would say the bond angle for water is probably one that's worth memorizing because it gets asked maybe a little bit more commonly than other ones, but understanding why it's reduced from 109.5 to 104.5 because the presence of 2 lone pairs here with lots of electron density pushing these single bonds down together towards each other. I hope the run through of the 3 scenarios for 4 electron domains has been helpful. If it has, please like the video and subscribe to the station. And as always, thank you so much for listening and watching.